I'm planning on going over a typical specific heat problem that you might see. This was also the specific heat problem that was in the exam review today that we didn't go over in class, so I wanted to go over it now. And then I'm planning on doing a mixing problem to show you how to set up a mixing problem, and this would be if you're taking, so the problem I'm going to do is if you're taking say water that's at a cup of water at one temperature and a cup of water at another temperature, mixing them together and determining what your final temperature will be. So once you've mixed these 2 cups of water together, what will be the temperature once it's reached equilibrium, and that means that the temperature is not changing anymore. So basically the water is mixed and they're both the same temperature. So let's start with this the specific heat problem. This is the type of problem that you'll likely encounter. And so this says that you have, so it just says you have a substance. So I might read the problem and then what I usually do with these word problems is I start writing down the information that's in the problem, because I feel like that often guides how to solve it. So, because a lot of times when you read just these word problems, your mind can go blank a little bit and you're not really sure where to start. So that's why I recommend reading the problem and then writing down the information that's in the problem to guide solving the problem. So this says, so you have a 28.86 gram of some substance. It just says a sample of a substance. It doesn't say what it is, and it's initially at 251.1 degrees Celsius. And then it says after absorbing 1237 joules of heat, the temperature of the substance is 193.2 degrees Celsius. So we want to know what is the specific heat of the substance. And this is kind of worded weird because it says after absorbing, but the temperature is lower, so it seems like it actually lost this heat, but we're just going to go with what's in the problem. So what we want to do is, first of all, this problem is talking about absorbing heat, but if it said that it was losing heat, or if the temperature is changing and it mentions specific heat, you probably need the heat equation. And so the first thing I would probably write down is the heat equation. So that is just the Q is equal to MCAT. So Q is equal to MCAT. And I like to remember it exactly like that, like Q is equal to MCAT. And I think this cat part is easy to remember. I mean, who doesn't like cats? So that's how I remember this. So this is actually a delta T. So this is the heat equation, if you haven't seen this before. And the Q is the heat that's either absorbed or lost from whatever substance you're looking at. The M is mass, C is specific heat, and delta T is the change in temperature. So this is the final temperature minus the initial temperature. And so what we want to do is just start writing down some things from this problem. So first of all, it says a 28.86 gram of sample. So that means that our mass is 28.86 grams. So we can write that down, 28.86 grams. And then if we continue reading, after absorbing 1237 joules of heat, so Q is the heat, so we would write down Q is equal to, and then I'm just going to set it equal to what's in this problem. So this is 1237 joules. And remember, joules is a unit for heat. So the temperature so it says the temperature was initially 251 degrees Celsius. So I'm going to put the initial temperature is equal to 251.1 degrees Celsius. And then it says the temperature of the substance after, and this says after it absorbed heat, but I think it's actually after it released heat. But the temperature final is equal to 193.2 degrees Celsius. So then, so if we look at this, like this is what we were given. And if we look at our equation, so it's asking us for the specific heat. Like it says, what is the specific heat of the substance? So if we look at this equation, we know Q, we know the mass, and we know T final minus T initial. So we know everything we need to figure out delta T. So we can just solve this equation for C. So if we do that, so we can solve the heat equation for C. So if we do that, C is equal to Q over the mass multiplied by delta T. And at this point, all we need to do is plug in the values that we were given, because we know Q, we know mass, and we know TF minus TI, which is delta T. So if we plug in Q, that is 1237 joules divided by, and then the mass is 28.86 grams. And then this is multiplied by T final minus T initial. So 193.2 minus 251.1. And we're going to end up with a negative number because Q is actually negative since we're losing heat. The temperature final minus temperature initial is negative, and so since we're actually losing heat in this problem, we're losing 1237 joules. Q is negative just to show that the direction of the heat is being lost, like the heat's being lost. So if we go ahead and calculate this, like you just put this into your calculator, this is equal to 0.740 joules per gram degree Celsius. So we've calculated the specific heat, and then this problem could possibly go a step further. It could say, well, based on this specific heat, what is this? Like, I mean, since substances have a certain specific heat, we should be able to figure out approximately what that is by looking at a specific heat table. So I'm going to look at the table in the textbook, which is the Timberlake General Organic and Biological Chemistry, 6th edition that I'm looking at. And if I look at the specific heat table, it's table 3-6. The closest, so just looking at some of these values, aluminum is 0.897 joules per gram degree C. Sodium chloride is 0.864 joules per gram degree C. So just if I just go off of this table, the closest substance that we have to this specific heat is sodium chloride. I don't know if this is sodium chloride or not, but if you were looking at a table online or in some other reference, you would probably have more values that you could look at to figure out what this is. But just looking at the table that we have in our book, this is the closest value to that. So that's the one that you would pick. Okay, so that's how you do a problem like this. And you might see different variations of this problem. Like it might say, like it might give you the specific heat and say, well, what's Q? Or what's the final temperature? And then you would just go through this the same way, only you would plug in different numbers because you're solving for something different. So now I want to do the mixing problem, so I'm just going to erase things real quick. For this mixing problem I want to go through, we have 2 cups of water. So I'm just going to draw. I like to draw pictures of what I'm solving for. I think it makes it easier to understand what you're solving. So let's say we have, so this is 1. So these are 2 cups of water. Here's 2. These are H2O. H2O is water. And what we're going to do is mix these together and then calculate what the final temperature is. So I'm going to write down some information about these. The volume of the first one is equal to 0.381 meters cubed, and the initial temperature, so I'm going to call this, so I'm calling this V1, so this is the volume of 1. I've just labeled this 1 and this one 2. So, and I'm going to call, this is the initial temperature, so I'm just going to call this T initial 1 is equal to 25 degrees Celsius. And then for the second one, I'm going to call this one V2, so this is the volume of the second one. This is equal to 0.132 meters cubed. And then the temperature initial of the second one is equal to 95 degrees Celsius. So we have 2 cups of water. One of them is 95 degrees Celsius. The other one is 25 degrees Celsius. And we want to figure out what the final temperature is when these are mixed together. So the way we can do this is, let's just draw these being mixed. So here's the cup, and we're dumping that one in, and we're dumping this one in. And what's going to happen here is this water that's at 25 degrees Celsius is going to warm up, and the water that's at 95 degrees Celsius is going to cool off. So the water that's at 95 degrees Celsius is going to lose heat, and the water that's at 25 degrees Celsius is going to gain heat. And if we assume that this container is perfectly insulated, so there's no heat loss to the outside, this is going to be, so this is perfectly insulated. All of the heat that's flowing from the hotter substance to the colder substance is going to happen inside this container. So what we can do with that is we can say, okay, well, we know that the Q represents heat, so we can say, well, Q1 is equal to Q2. But then we need to put a sign on one of these because we need to indicate the direction of the heat flow. So the heat is flowing from the hotter water to the cooler water. So the T2, the heat is flowing from the water in cup 2 to the water in cup 1 once they're mixed together. So when the heat flow is away from or out, we indicate that as a negative. So we indicate that if something's cooling off or losing heat, it has a negative sign, and if something's warming up or gaining heat, it's positive. And there's different conventions for this, but that's the convention that we're going to use here. So now what we want to do is write, well, what's our heat equation? So remember, the heat equation is Q is equal to MCAP. So what we can do with this is we can say, well, we know that Q1 is equal to negative Q2, so we can just put this directly in this MCAP part of the equation, so mass times specific heat times delta T. We can put that directly into this equation in place of Q1 and Q2. So for Q1, and I'll write this out, so Q1 is equal to M1 C1 and instead of writing delta T, I'm gonna actually do the temperature final. And remember, both of these are at temperature final. This is going to be they're going to both be the same temperature because they're mixed together, and when they're at equilibrium, they're going to be the same temperature. So this is temperature final minus, and then we're looking at 1, so this is minus 25 degrees Celsius. And then Q2 is equal to, now we have the mass of 2 multiplied by C2, and this is going to be, and this is negative, so this is negative, remember that. So this is temperature final minus delta T, so temperature final minus 95 degrees Celsius. And then what I want to do with this is I want to multiply through the negative sign. So I'm going to say Q2 is equal to M2 C2 95 degrees Celsius minus temperature final. So now I have an equation for Q1 and Q2. So what I want to do now is just set them equal, like set this part of the set this equation equal to this equation. So if I do that, I have M1 C1 temperature final minus 25 degrees Celsius, and this is equal to M2 C2 95 degrees Celsius minus temperature final. So this is the equation we want to solve for the final temperature. And we know everything except for the final temperature. And I take that back. We actually weren't given the mass, we were given the volume. So what we want to do with that is, we know this is water, and so we want to use so if we have the volume and we know what the substance is, we know what the density is. So we know what the density of water is. So since we know the mass, since we know the volume and we know the density, we can get the mass. So the density of water is equal to 1,000 kilograms per meter cubed. And density, so rho H2O, is equal to mass over volume. So we can get the mass by just saying the mass is equal to the density of water multiplied by the volume. So then what we can do is just plug this directly into our equations for the mass. And I'm going to erase some things real quick. We have this equation, and I'm going to rewrite a few things. So first of all, since the two substances that we're mixing together are both water, that also means, so we know that they have the same density, but we also know that they have the same specific heats. And so I can say that C1, the specific heat of 1, is equal to C2. So I'm going to go ahead and cancel the specific heat out of this equation because they're the same, so they're just going to cancel out. And then I'm going to put in the density multiplied by the volume for the masses. So M1 is equal to M2, and this is equal to the density of water multiplied by the volume. So this is actually, so this would be M1 is equal to that, and then M2 is equal to the density of water multiplied by the volume of the second one. So I'm going to plug these in for the masses. So for mass 1, I have the density of the water multiplied by the volume, and then I have temperature final minus 25 degrees Celsius. And this is equal to, and I'm going to put this in for the mass of the second one, so the density of water multiplied by the volume of the second one, and this is multiplied by 95 degrees Celsius minus the final temperature. So now I want to solve this equation for the final temperature. And well, actually, first what I want to do is cancel out the density, because I have the density, the same density term on both sides, so I can just cancel that out. And then I want to solve this for the final temperature. So what I need to do is get the temperature final on one side of the equation so I can solve for it. So what I need to do is multiply the V1 through this part of the equation and then V2 through this part of the equation. So I have V1 multiplied by temperature final minus V1 multiplied by 25 degrees Celsius, and this is equal to V2 multiplied by 95 degrees Celsius minus V2 multiplied by the final temperature. So now what I want to do is add so I want to get the final temperature terms together, and I want to get these two terms together. So what I'm going to do is add this term to this side, and I'm going to add this term to this side. So if I do that, I have V1 temperature final plus V2 temperature final, and this is equal to 95 degrees Celsius multiplied by V2 plus 25 degrees Celsius multiplied by V1. So now what I want to do is pull the final temperature out of this term so that I can divide the V1 plus V2 over and calculate temperature final. So if I pull the final temperature out of this equation, I get TF multiplied by V1 plus V2, and this is equal to this 95 degrees Celsius multiplied by V2 plus 25 degrees Celsius multiplied by V1, and then I can just divide this term over. So if I do that, I have that temperature final is equal to 95 degrees Celsius multiplied by V2 plus 25 degrees Celsius multiplied by V1 divided by V1 plus V2. So now the last thing I want to do is just put the values into this equation and solve for the final temperature. So I'm going to erase some things real quick. So I'm going to put in my values. So I have the temperature final is equal to 95 degrees Celsius, and this is multiplied by V2, which is 0.132 meters cubed, and I have plus 25 degrees Celsius, and this is multiplied by V1, which was 0.381 meters cubed, and then this is all divided by V1 plus V2. So I have 0.132 meters cubed plus 0.381 meters cubed. So then just looking at this equation, the meters cubed are all going to cancel out, and I'm left with degrees Celsius, which is what I want because I'm solving for a temperature. If I had have ended up with something with different units, say if I had have ended up with units of, say, degrees Celsius over grams or degrees Celsius over, or even if it was still over meter cubed, then these are the wrong units for what your temperature here. So you know that you did something wrong in deriving this equation, and so you need to go back and check everything. So if you plug these numbers into if you just plug this into your calculator, you get that the temperature final is equal to 43 degrees Celsius. So I hope that helps. These mixing problems are all pretty similar, So for instance, if you're, like this one was mixing 2 cups of water, but if you were, let's say you had water that's at room temperature, and you add a hot piece of metal, so let's say, I don't know, this is, like let's say you have a forge and you're like cooling off a blade or something. So you would put it in water to cool it off. So this is the same concept, because when you put this hot metal in the water, you're losing heat from the metal to the water. And we're going to assume this container is perfectly insulated again. So I'm just going to say insulated. So there's no heat loss from the container. So all of the heat that's lost from the metal is transferred to the water. So this can be written as Q. So we're losing heat from the metal to the water. You would set up and solve this problem the same way as the one we just did. It would just look a little bit different because you're looking at metal and water, and so first of all, your specific heat wouldn't cancel out because each of these materials have a different specific heat. But going through and setting up the problem is still the same process. And so with this, we would have Q water is equal to Q of the metal. So the heat lost from the metal is equal to the heat gained by the water. And then we have a negative sign on the metal because the metal is losing heat. So then you would do the same thing where we know that Q is equal to MCAT. And so you would just go through and set the MCAT for the water is equal to the negative MCAT for the metal, and then just go through the same process. So I hope this was helpful. Thank you.